And for PAM, I do exactly the same thing. I got the expression, I compare them. So this can help as a first step in deciding which technique should I use or which one should I not use, okay, as the case may be. Easy. So that is pulse-based. Those are very good, particularly if you're looking at things like sensor networks, low energy system. The data rates might not be the best, but they are very good. They are robust as well because they're just based on pulse level, energy levels. We look at energy, done. Non-linearity, not so much of an issue when it comes to pulse-based. But when it comes to continuous time, then we have to be very careful about non-linearity. Now, to do this, I'm going to start again by writing on the board very quickly. Are we familiar with things like QAM, modulation? Everybody? QAM. Very good. So let's say this is a QAM constellation. Let's say just 4 QAM. So I've got my I, I've got my Q. I've got just 4 points. This could be, I don't know, AN. This could be BN. Because this is both real and imaginary. I cannot possibly use it as it is for optical modulation, for intensity modulation. So I need to do something to it. Okay? Therefore, I need to use what is called subcarrier intensity modulation. In other words, I put this information on a carrier. Okay? Just as the way you do in RF, put on the carrier, but the carrier frequency is going to be very small in baseband. It will be in the kind of the same order as your symbol rate. Okay, so it will be in the baseband. So that's what we do. I will use the block diagram. See here. Let's look at just one for now, just one. Okay, this is a basic modulator. Okay, I've got my information coming in, and I've got a carrier, cosine in this case. I multiply them together. This is just a pulse shaping function, like a root raised cosine pulse shaping, just to make sure that we have a small bandwidth. Okay, so you multiply them together, and you get your message. Essentially, what we are doing here is you got your data, you modulate it with a carrier, and you get modulated signal out. Okay, that's what we do in RF as well. That's the basic of modulation, except that this carrier has to be in very close to baseband. Okay, it has to be in the passband of your system. All right, so we do just one, we modulate it. By the time I do multiple, I do for cosine and I do for sine, because the real one here is the one for the cosine, as we know, and the Q one here is the one for sine. So that's how I do it. That means wherever I have the cosine, the information here is this constellation point AN, the real one, and for the sine, it's going to be the BN here that I have. It's very similar to what we do in RF. The only difference is the carrier frequency, as I mentioned. We can do just for one, that's just single subcarrier, or we can have multiple subcarriers. So we can add them together, and then we have our signal. Does that make sense, what I'm trying to do? Now, the basic concept here, when we get to OFDM, we'll talk about. So that's what we do for subcarrier intensity modulation. And then we go to the front end, as I explained. That's our MT. Because this signal, this cosine and sine, they are still unipolar. Okay, so we need some DC. We need to put it at the bias point. If you remember this graph, this DC, this one here, is this point. That's DC, because the signal we are getting by the time you add all of this together is unipolar, but real. All right? And then so it becomes something like this. And that's what we get. And that's subcarrier modulation. You get to the receiver side, you do exactly the opposite. Photodiode, you do the opposite and you get your information out. It's as simple as that. Any questions? Have I lost anyone? Good. So, again, yeah.
What you said about the transmitters absolutely makes sense, but all of that is dependent on the possibility of the receiver side to detect. I mean, the sensitivity of your photodiode is basic, the pre-amplifier design. So how do you define the measurements, like the measures needed to be implemented in the receiver side, so that we can also get all the information and not filter them out?
Okay, very good. So the point is, because this is, as I mentioned, this is intensity modulation, right? So the information is on E squared, right? That's where it is. Now, the photodiode we use here is what is called a square law device. It responds to the square of the field. All right? So remember, it will be very clear this way. So I'll explain this way. We said our P out, the power out, is some average power, 1 plus beta MT, okay? So this MT is the message, all right? Now, at the output here, at this point, so your photoreceiver gives you a current, which is the same thing as a constant, right, times the power that is out here. If I assume, lossless scenario, because it's linear, it responds to the square of the field. The square of the field is proportional to the power, so that's why I just use P here, okay? Does that make sense? Yeah. So if I take this one out, and then I put my P out here, 1 plus beta MT, that's what I get. So this is a DC term, and I put a filter. That's why I've got a filter, to get rid of the DC. Then I just got my information. So you just do what you do in baseband demodulation for RF. Make sense? Any more questions? Good. So we continue. And then if we have multiple, again, we do multiple, and we get our information. That is how we can use things like QAM in optical, based on subcarrier intensity modulation, okay? We can have multi-carrier, we can have single carrier, that's fine. Again, we look at the spectral efficiency, you walk it through, efficiency is going to be 2M. The steps are there, okay? Where M is the number of bits per symbol. In this case, I've got to highlight or mention that this is multidimensional. We have the I dimension, we have the Q dimension. When it comes to palm, it's just 1. We have only amplitude. When it comes to on-off keying, it's just 1. Okay, 1. So this is multi. That's why we can increase spectral efficiency by that. Okay, and that is what we get for the spectral efficiency. Pros and cons, I leave that. For now, you can have a read of why it is good and why it might not be so good, depending on what you are trying to achieve. Okay, but note that it doesn't give any more spectral efficiency than your regular palm. Okay, because people tend to make that confusion. That's highly spectral efficient. Yes, it is, but no more than your regular palm that you get from QAM. Okay. Then the next one is called the cap. Now, there's a bit of history when it comes to cap. And it seems that in optical, we tend to use whatever has been used in radio and then try to use for visible light conducting as well. Okay? So there's a bit of history when it comes to cap. The idea behind cap is very straightforward. Remember, we said our message, we modulate with the carrier, and then we have information out. This is our MT. Well, that's fine, not a problem. Let me just modify this a little bit. I put a pulse shaping, GT. Okay? This is just to make sure it is root raised cosine filter. When it comes to cap, there's just a little twist. I said, okay, if I get this GT and the carrier as a single block, here there are two different things. So if I combine GT and this guy, the carrier, together as one block, therefore, all I have is just my data goes into a block, and then I have my MT out. Okay? Here is now GT times the carrier frequency. Do you understand? I just multiply them as a separate block. It's essentially the same thing. Do you understand? Instead of doing them separately, I combine these two together first, and then I put my data to it. Why do we do that? Because we believe that because the carrier frequency is so low, it's in baseband, we can use FIR filters. Okay, so if you design them as a filter, it's a lot easier. It's just about simplicity. This ordinarily would be a local oscillator. You understand? But I don't need that high frequency. So I can just use a filter to design a cosine wave or a sine wave and then multiply them with my root raised cosine. And that's the only difference between a cap and subcarrier intensity modulation. Every other thing remains the same. It's just that we don't separate the carrier and the pulse shaping filter. That's all. That's the only difference between them. Okay? And you can see that's what the equations are saying in here. So that's essentially what is there. Therefore, in terms of spectral efficiency, they are going to be exactly the same thing because there's the same system, okay, between cap and SIM. No difference between them. So you still have to have your DC. Everything is the same. Sorry, this is just some artifact from the PDF converter. So that's exactly the same thing. And again, I put some advantages of using CAP and some disadvantages of using CAP. One thing I've got to say is that when it comes to CAP, yeah, this is just an example. Okay, we got your sine wave, you got your pulse shaping filter, and the red one is the combined. When I combine them together, then that's what you get for the red one. So that becomes the overall. That's the only reason we do it. But I've got to mention that that simplicity can be lost because when you do CAP, because it's very sensitive to nonlinearity, you often have to implement equalization. And when you do equalization, you increase complexity. So what you gain from one hand, you lose it, on the other side. Okay, just be aware that's not that straightforward. Okay, and again, CAP design, it could be single carrier, just like SIM, or it could be multiple carrier as well. I've talked about the advantages of this one. Then we can have MCAP, just as we add multiple subcarrier intensity. So that's in a nutshell how CAP works. Okay. Again, to talk about OFDM, have we heard about OFDM? Anybody? Okay, very good. So if we've heard about it, well, I'll come back to this diagram to explain. Here, I've said we can have multiple subcarriers. And I've not said anything about the relationship between the subcarrier frequencies, right? When it comes to OFDM, the only difference is these subcarrier frequencies have to be orthogonal. Okay, when I say orthogonal, I'm guessing we all know what I mean by orthogonal, right? That is, they don't give each other crosstalk. That's the only difference between them. Okay, that's all. In analog, when you implement OFDM in analog, it's exactly the same thing as a SIM, except that often we implement OFDM in digital domain. Why? Anybody? Why? I'm sure we've all done Fourier series or Fourier transform at some point, yes? Exactly. So what does Fourier series tell us? Fourier series, what does it say? If you have any signal xt, right, it means it can be decomposed into the weighted sum of its harmonics, correct? Exactly. So we can have summation ai cosine I of whatever, omega t, okay, plus bi sine I omega t. If you look at this very well, it looks pretty much like this one. Do you understand? We have cosine, and I have sine. I have cosine, I have sine. This what's it called? This AI and the BI, they become your constellation point from QAM. You understand? So this AI and BI, they become your constellation point from QAM. Therefore, if I want to implement OFDM, naturally, from Fourier series, these are orthogonal. Okay? So if I want to implement OFDM, all I've got to do is carry out FFT and IFFT. So because I'm starting from here, so I'm going back this way, so I have to do IFFT, okay, with my constellation symbol. That's all. That's the only difference because we do it in digital domain. All right? Because they are all the same. Conceptually, SIM, CAP, OFDM are exactly the same thing with these little differences there. Therefore, all of them have the same spectral efficiency, okay? And you can see I've put some examples there of how to find the spectral efficiency for OFDM. That's one thing I really have to mention here, okay, for OFDM. And that is, normally when you do this operation, IFFT, the output is complex, right? But we can take advantage of the symmetry of IFFT, and it's called the emission symmetry. Basically, if you've got, let's say you've got XT, and you do IFFT of this guy, you get a complex output. Okay? So what you can do is that you replicate it, xn, you put 0, and then you put the complex conjugate. Okay, there. That is, and then you flip it. You flip this guy. That is a property, that is a symmetric property of IFFT itself that we can use. So that if you do this, and then you carry out IFFT, the output becomes real, okay? That's all. But it's still going to be unipolar. Sorry, it's going to be bipolar at that point. And then we add our DC. That's the only difference. Now, there's a lot of misconception when you read literature that by the time you do this, emission symmetry, you lose half of the bandwidth. That is not true. You understand? That is absolutely not true. This emission symmetry is just a mathematical artifact, and I can tell you where it's coming from. Just like this. If you have cosine of omega ct, like that, okay? If you break this into its Fourier transform, right, or in exponential, this becomes ej omega t half into plus, right? ej omega t, like that, correct? That's true, right? But what is the frequency here? It's just 1 omega. But I have both the real, the positive part and the negative part. So that's what we replicate with emission symmetry. You get the point? Exactly. See, this is the real time domain, okay? But when it comes to this complex domain, I've got 1 here, and I've got 1 here. So this is 0. I've got 1 on the positive, 1 on the negative. But the frequency is still omega. So we replicate this with emission symmetry, but we're not losing any bandwidth, okay? And that should be the end of my talk today. So I'm happy to take questions.
First, let's thank you.